This topic will cover how to calculate the expected value or mean and variance of a continuous random variable after a linear transformation. Recall from last lesson the formula for the mean or expected value of a continuous random variable, the variance and the standard deviation. We're now going to consider, for a continuous random variable x, what the expected value would be of ax plus b, where a and b are constants. So we're going to do this by calculating the expected value of ax plus b, which is ax plus b multiplied by the probability density function and then integrated. This can be split up in the way that integrals are usually split up. So we have the ax part here and the b part here. Now, because a and b are constants, these can be pulled to the front of the integral. However, anything involving x must stay inside. So we're left with a times the integral of x f of x dx plus b times the integral of f of x. Now we know that this part here, the integral of f of x, must equal 1, assuming that the integral has been taken from negative infinity to positive infinity. This is because the area under a PDF is always equal to 1. We also know that this part here is just the expected value of x. So therefore we have that this becomes e times the expected value of x plus b. In other words, the expected value of ax plus b can be calculated by taking the expected value of x, multiplying by a and adding b. We're now going to consider the variance of ax plus b. Now, using the formula that the variance of x is the expected value of x squared minus the expected value of x all squared, we can say that this is the expected value of ax plus b squared minus the expected value of ax plus b all squared. So this here is the expected value of ax plus b squared, and this here is the expected value of ax plus b and then squared. So here what we have done is expanded ax plus b squared and kept it inside the integral. Here we've just used the formula from the previous slide for the expected value of ax plus b, and because it's squared we have squared this. So this becomes a times the expected value of x plus b and then squared. Next, we can split this into 3 separate integrals. So we have a squared x squared f of x integrated, we have 2abx f of x integrated, and we have b squared f of x integrated. Here we have just expanded this bracket out, so multiplied this bracket together. On the next line, we have just taken out any constants, for example, a squared here, 2ab here, and b squared here, leaving anything involving x inside the integrals. And now we can see that this integral here, the integral of x squared f of x, that is just the expected value of x squared. This integral here, the integral of x f of x, that's just the expected value of x. And this here is just 1, because we've got the integral of f of x from negative infinity to positive infinity. So this just becomes b squared here. For the moment, these parts at the end have all remained unchanged. Finally, we notice that quite a lot of these things cancel. For example, we've got 2ab ex here, we've got minus 2ab ex there. We've also got b squared and minus b squared, which are cancelling. So all that is left is just a squared times the expected value of x squared minus a squared times the expected value of x all squared. Because both of these terms involve an a squared, we can factorise this here. And we notice that what is left inside the bracket is just the variance of x. So what we have is that the variance of ax plus b just becomes a squared multiplied by the variance of x. So we notice that we've multiplied the variance of x by a squared, and the b has not affected the variance at all. This is because adding a constant onto something doesn't change how spread out the variable is. So the plus b has not affected anything here. However, multiplying by a constant does affect the variance. So this brings us to these two formulae. We have for a continuous random variable x that the expected value of a linear transformation ax plus b just becomes a times the expected value of x plus b. And for the variance of ax plus b just becomes a squared multiplied by the variance of x. From this, we can conclude that therefore the standard deviation of ax plus b will just be a times the standard deviation of x. This is just because the standard deviation is the square root of the variance. So the a squared in this case is square rooted just to become a. In this example, we are given a continuous random variable x and its probability density function given below. We want to find the value of the expected value of 3x minus 5. So before we start, we need to calculate the expected value of x. So this can be done by finding the integral of x times f of x for each of the parts of the function. So we're integrating x times 2x over 15 from 0 to 3. Then we're integrating x times 1 minus x over 5 from 3 to 5. This gives us 2.667. We're now going to use the formula that the expected value of ax plus b is just a times the expected value of x plus b. So in this case, we are going to multiply by 3 and subtract 5. The expected value of 3x minus 5 is therefore 3. In this example, we're going to consider a 100 centimetre length of pipe, which is being cut into two pieces, a long pipe and a short pipe. The long pipe has an average length of 80 centimetres and a standard deviation of 2 centimetres. The leftover piece is then being used as a shorter pipe. We want to find the mean and the standard deviation for the length of the short pipe. So in any question like this, the first thing is important to do is to define what the variables are going to be. So in this case, we're going to let L be the length of the long pipe. It's important not just to say long pipe, we need to say length of long pipe. We're going to let S be the length of the short pipe. So we already know that the expected value of L is 80 centimetres. We also know the variance of L is 2 squared, so 4. We want to find the expected value of S and the variance of S. So the transformation that takes us from L to S is that the length of a short pipe is 100 minus the length of the long pipe. So in this case, if we're considering the AX plus B, we can see that A is minus 1 and B is 100. This is like minus 1L plus 100. So we now want to consider what the expected value of S is going to be. So we're looking for the expected value of 100 minus L. So we know using the formula this is going to be A times the expected value of L plus B. So in this case it's going to be minus the expected value of L plus 100. So this is going to be minus 80 plus 100. So 20 is the expected value of the length of the short pipe. We need to make sure we give units here, so that's going to be in centimetres. We're going to consider first of all the variance of S. Now we know that the formula for variance of AX plus B is just A squared times the variance of whatever X is. So in this case we're going to just multiply the variance of L by -1 squared. So we know that this is just going to be the variance of L, which is 4. So therefore, the standard deviation of S is going to be the square root of 4, which is 2 centimetres. So the standard deviation for the short pipe is actually the same in this case as the standard deviation for the long pipe. In this example, we have a random variable x with a probability density function. This function is 1 over 21 x squared for values of x between 1 and 4, and it's 0 otherwise. We want to find the expected value of 7 over x. So for this, we're going to find the integral of, and because we're looking at the expected value of 7 over x, it's going to be the integral of 7 over x multiplied by the probability density function, 1 over 21 x squared dx. This is going from 1 to 4. Since it's 0, otherwise we don't need to integrate anything else. So here we are finding the integral from 1 to 4 of, and we're going to get 7 over 21, which is 1/3. X squared over x is just x dx. This gives us 1/3 x squared over 2, so 1/6 x squared between 1 and 4. So we're going to calculate f of 4 minus f of 1. This gives us an answer of 2.5. So the expected value of 7 over x is 2.5. Now complete exercise 4C on page 62.